This is Sleepy Space, a slow space story to help you fall asleep. You flip a switch. Light fills the room. It feels instant, so instant that you never question it. You turn on a lamp, and the world simply appears. The walls, the floor, the shapes around you. There is no sense of motion, no feeling of travel, no delay that your mind can detect. Light seems to arrive fully formed. But that feeling is misleading, because light does not appear. It travels, and it always has. The only reason it feels instant is because your brain was never built to notice the delay. In everyday life, the distances around you are small enough that light crosses them before your senses can react. So the illusion holds, the room brightens, the screen glows, the moment feels immediate. But immediacy is not the same as instant. Light moves at a fixed speed, a speed that never changes, a speed that is woven into the structure of the universe itself. It moves at just under 300,000 kilometers each second, fast enough to circle the entire planet several times in the span of a heartbeat, fast enough to feel infinite, and yet still finite. Here on Earth, that difference barely matters. The delay is too small to notice. Light crosses a room in a tiny fraction of a second, so small that your brain cannot register it. When you turn on a lamp, the light appears to arrive all at once. Even across much larger distances, the effect still holds. Light can travel between distant cities in far less time than it takes to blink. Faster than your nervous system can process most sensations. For almost every moment of human life, light simply seems to be there. Because of this, people did not always think of light as something that traveled. For much of history, it seemed obvious that light was instantaneous. Aristotle believed it arrived without delay. Descartes argued the same. You open your eyes and the world is visible. No waiting, no lag. The universe appears complete. That assumption lasted for centuries, until a quiet observation began to challenge it. In the late 17th century, an astronomer named Ole Rømer studied the moons of Jupiter. He noticed something subtle. The timing of their eclipses did not remain perfectly consistent. Sometimes the eclipses arrived later than expected, sometimes earlier. The difference depended on where Earth was in its orbit. When Earth was farther away, the eclipses lagged behind. When Earth was closer, they arrived sooner. The moons themselves were not changing. The delay belonged to the light. Rømer realized that light took time to cross space. Greater distance meant greater delay. Light was not instantaneous. It moved. It had a speed. And once that became clear, distance and time could no longer be treated as separate ideas. This is where the universe begins to feel unfamiliar. On Earth, distance and time feel independent. You can cover the same distance quickly or slowly. The distance itself does not change. But in space, distance reveals itself as time. The farther something is, the longer its light has been traveling. You never see objects as they are. You see them as they were. The light reaching your eyes left its source moments ago, or seconds ago, or much longer than that. In daily life, this delay does not matter. It is too small to notice. But the effect scales. As distance increases, the delay increases with it. until delay becomes the defining feature of observation itself. Every object you see beyond your immediate surroundings exists slightly in the past. The screen in front of you is already older by the time its light reaches your eyes. The lamp across the room belongs to an earlier moment, however small that difference may be. And beyond Earth, the gap grows quickly. Out in space, distance is no longer measured by meters or kilometers in any meaningful way. Those units become abstract. They lose their ability to communicate scale. So astronomers changed how they thought about distance. They stopped describing space only in terms of length and began describing it in terms of time. Not the time it would take a spacecraft to travel, not the time it would take a human, the time it would take light. Light is the fastest possible messenger in the universe. The quickest way information can move from one place to another. And once you begin thinking this way, a quiet truth becomes impossible to ignore. Everything you see in the night sky is already a memory. Stars are not where they appear to be. They are where they were when their light began its journey toward you. Some have shifted since then. Some have changed. Some may no longer exist at all. And yet you still see them, because their light is still on the way. This is what makes space fundamentally different from Earth. Distance is no longer only about where something is. It is about when you are seeing it. Space becomes inseparable from time, and light, moving at its fixed and unchanging speed, becomes the thread that binds them together. Once you understand this, the universe stops being a place you look at. It becomes a record, a history written in light. And to understand why astronomers abandoned ordinary distance measurements entirely, we need to follow a single photon, a journey that begins here, in this room, with you, a light second. That's the baseline unit. The distance light travels in 1 second, and that distance is roughly 300,000 kilometers. To be more precise, it's 299,792 kilometers, but we can round to 300,000 for the sake of comprehension. Your brain doesn't do much better with 299,792 than it does with 300,000 anyway. 300,000 kilometers in 1 second. To put that in perspective, Earth's equator is about 40,075 kilometers around. If you could somehow wrap a tape measure around the planet at its widest point, that's the number you'd get. Now, light moves so fast that in a single second, it could circle the entire Earth not once, not twice, but approximately 7.5 times. 7 complete loops around the planet, plus a little extra, all within the span of 1 heartbeat. Think about that for a moment. 1 second, 1 Mississippi. That's all the time it takes for light to wrap itself around the Earth 7.5 times. This is why, when you flip a light switch, the room illuminates instantly. The light doesn't need to travel far. Even in a large room, maybe 10 or 20 meters across, light covers that distance in a fraction of a microsecond. It's so fast that there's no perceptible delay. Your neurons can't fire quickly enough to notice the gap. To your senses, the light just is. But the speed is real, and it does matter, even here on Earth. We just have to look at the right systems to see it. Consider fiber optic cables. These are the thin strands of glass that carry internet data across continents and beneath oceans. When you send a message from one side of the planet to the other, that data travels as pulses of light through these cables. And even though light is the fastest thing in the universe, it still takes time. A signal sent from London to Sydney travels roughly 17,000 kilometers through undersea cables. At light speed, that takes about 56 milliseconds. Not long, but measurable. Gamers notice it, financial traders notice it. High-frequency trading systems are built around shaving off even a few milliseconds of delay, because light, fast as it is, still obeys the rules. Then there are satellites. When you make a phone call via satellite, your voice is converted into a radio signal, which is a form of light, and sent up to a satellite orbiting roughly 35,000 kilometers above the equator. The signal travels up, gets relayed, and comes back down to someone else on Earth. That's 70,000 kilometers total, sometimes more depending on the geometry. At the speed of light, this takes about a quarter of a second. That's why satellite phone calls have that characteristic delay. You say something, and there's a pause before the other person responds. It's not a processing delay. It's light, traveling at its maximum speed, taking time to cross the distance. This is the first hint that even light, for all its speed, is not instantaneous. It's bounded by distance. The farther it has to go, the longer it takes. And in space, the distances grow so large that even light starts to feel slow. Let's stay on Earth for a moment longer and think about what happens in that single second. A photon leaves the bulb in your lamp. It travels outward in all directions, moving at 300,000 kilometers per second. It strikes the wall. Some photons are absorbed. Others bounce off and scatter. Some of those scattered photons reach your eye. Others continue bouncing around the room, hitting furniture, the ceiling, the floor. They lose energy with each interaction until they're eventually absorbed or converted into heat. All of this happens in fractions of a second, but it happens in time. Real, measurable time. And if you could somehow watch a single photon's journey in slow motion, slowed down by trillions of times, you'd see it moving. Not teleporting, not instantly appearing. Moving through space at a fixed speed. Now imagine scaling this up. Not a room, but a city. Not a city, but a continent. Not a continent, but the whole planet. Light still moves at the same speed. It doesn't speed up for larger distances. It doesn't slow down for smaller ones. It just moves. 300,000 kilometers per second. Always. Everywhere. This constancy is part of what makes light so useful for measuring cosmic distances. It's reliable, predictable. You can count on it. Unlike sound, which changes speed depending on the medium it's traveling through, light in a vacuum always moves at the same rate. It's a universal constant. The speed of light in a vacuum is represented by the letter c in physics equations. It is one of the most fundamental numbers in the universe. But here's the thing. 300,000 kilometers per second sounds fast. It is fast. It's the fastest possible speed. But when you're trying to measure the universe, even this speed starts to seem modest, insufficient, almost quaint. Because if light takes a quarter of a second to bounce off a satellite 35,000 kilometers away, how long does it take to reach the moon? The moon sits almost 400,000 kilometers from Earth. How long to reach the sun, which is 150 million kilometers away? How long to reach the nearest star beyond the sun? The answers to these questions start to stretch time in uncomfortable ways. A second becomes seconds. Seconds become minutes. Minutes become hours. Hours become years. And years become thousands of years, then millions, then billions. 7.5 times around our entire planet in a single second. It sounds impossibly fast. It is impossibly fast by any human standard. And yet, that's just the beginning of understanding how small this speed becomes when measured against the cosmos. The moon is close. At least, it feels close. You can see it with your naked eye. It looks large in the sky, sometimes bright enough to cast shadows. On a clear night, you can make out details on its surface, the dark patches, the lighter regions. It seems almost within reach. But the moon sits 384,400 kilometers away from Earth on average. That distance varies slightly because the moon's orbit isn't a perfect circle, but roughly 384,000 kilometers is the number we work with. And at the speed of light, crossing that distance takes about 1.28 seconds. Just over 1 second, 1 light second and a little bit more. That might not sound like much. It isn't much in the grand scheme of things. But it's enough to matter. It's enough to create a noticeable delay. And that delay was very noticeable to the astronauts who traveled to the moon and the people who spoke with them from Earth. When Neil Armstrong and Buzz Aldrin walked on the lunar surface in 1969, every word they spoke had to travel back to Earth as a radio signal. Radio waves are light, different frequency, same speed. And those radio waves took 1.28 seconds to make the journey from the moon to mission control in Houston. Then, when someone in Houston responded, that response took another 1.28 seconds to travel back up to the moon. The total round-trip communication delay was about 2.6 seconds. Every single exchange had this gap built into it. Armstrong would say something. Houston would hear it 1.28 seconds later. Houston would respond. Armstrong would hear that response 1.28 seconds after it was sent. Nearly 3 seconds total. You can hear this delay in the recordings. There's a pause between question and answer that feels just slightly too long. It's not an awkward silence. It's physics. It's the speed of light, crossing the gap between two worlds. This was humanity's first real experience with cosmic communication delay. Before the moon landings, nearly all of our communication happened on Earth, where light's travel time was imperceptible. A phone call across the country had no noticeable lag. Even satellite communication delays were brief enough that people adapted without thinking about it. But the moon was different. The moon was far enough that the delay became part of the experience. You couldn't have a fluid, natural conversation. You had to wait. You had to account for the gap. And this is where the strangeness of light travel time starts to become emotionally real. Because that 1.28 second delay means something profound. It means that when you look at the moon, you're not seeing it as it is right now. You're seeing it as it was 1.28 seconds ago. The light that left the moon's surface just over a second ago is only now reaching your eyes. If something happened on the moon right this instant, you wouldn't see it for another second and change. If the moon somehow vanished, it would still appear in the sky for 1.28 seconds, before you noticed its absence. This is the first real demonstration of a principle that defines all of astronomy. We never see things as they are, we see them as they were. Every observation is an observation of the past. The farther away something is, the deeper into history we're looking. For the Moon, the delay is trivial. 1.28 seconds is nothing. It's a blink. But the principle holds. And once you leave the Moon and venture farther into space, the delays stop being trivial. The concept of a light minute becomes useful here. A light minute is simply the distance light travels in 1 minute. At 300,000 kilometers per second, that works out to 18 million kilometers. 18 million. The number is starting to grow uncomfortable. It's harder to visualize, harder to relate to anything in human experience. But let's try anyway. Imagine you're standing on Earth and you want to send a message to a spacecraft that's 18 million kilometers away. You transmit the message. It travels at the speed of light, the fastest possible speed. And it takes 1 full minute to arrive. Then, if that spacecraft sends a response, that response takes another minute to come back. 2 minutes total. Round trip. 2 minutes doesn't sound like much. You could make a cup of tea in 2 minutes. You could walk to the end of your driveway and back. But in terms of communication, 2 minutes is an eternity. It means you can't have a conversation. You can't ask a question and get an immediate answer. Every exchange is separated by this mandatory gap, imposed by the speed of light and the distance involved. This is the reality for space agencies operating probes and rovers. When the National Aeronautics and Space Administration sends a command to a rover on Mars, which can be anywhere from 4 to 24 light minutes away, depending on where Earth and Mars are in their orbits, there's a significant delay. If something goes wrong, if the rover encounters an obstacle or starts to tip over, there's no way for human operators to react in real time. The information takes minutes to reach Earth. The corrective command takes minutes to get back. By the time anything happens, the situation has already unfolded. This is why Mars rovers are semi-autonomous. They have to be. Light, even at its maximum speed, is too slow to allow for real-time control. The distance imposes a delay that can't be overcome. And the Moon, at just over 1 light second, is the closest natural object beyond Earth. It's the nearest thing we can look at in the night sky, other than the occasional passing asteroid or comet. And even the Moon is far enough that we see it in the past. Not the distant past, not the ancient past, but the past nonetheless. That delay, that glimpse into the past becomes more profound the farther we look. And the Sun, our nearest star, offers the first truly unsettling demonstration of this cosmic time lag. The Sun is 8 light minutes and 20 light seconds away from Earth. That distance, in more conventional terms, is about 150 million kilometers. But we're learning to think in light travel time now, so let's use that. 8 minutes and 20 seconds. That's how long it takes light to travel from the surface of the Sun to your eyes. 8 minutes doesn't sound like much. It's less time than it takes to brew a proper pot of coffee. It's shorter than most popular songs. It's a fraction of your morning commute. But in cosmic terms, 8 minutes represents a distance so vast that no human has ever crossed it. No human likely ever will. When you look at the Sun, assuming you're doing so safely through proper filters or indirectly, You're seeing it as it was 8 minutes and 20 seconds ago. Not as it is now, as it was. The photons that left the sun's surface more than 8 minutes ago are only just now reaching Earth. They've been traveling through the vacuum of space, moving at the maximum possible speed, and they're only now arriving. This creates a strange situation. If the sun suddenly vanished, if it somehow blinked out of existence right this instant, we wouldn't know for 8 minutes and 20 seconds. The Earth would continue to orbit the spot where the sun used to be. The sky would remain bright. Plants would continue photosynthesizing. Everything would seem normal. And then, 8 minutes and 20 seconds later, the last photons from the sun would arrive. After that, darkness. Sudden, total, and permanent. Of course, the sun isn't going to vanish. Stars don't work that way. But the thought experiment reveals something important about the nature of distance and observation. There is no now in space. There is only then. Everything we see happened in the past. The farther away something is, the older the light. The sun is our closest star. It's the star we know best. We've studied it for centuries. We've sent probes to observe it up close. We understand its composition, its temperature, its life cycle. And yet, we live in its past. We orbit a version of the sun that existed 8 minutes ago. We bask in light that's already 8 minutes old by the time it warms our skin. This delay affects everything we know about the sun. Solar flares, for example, are violent eruptions of energy from the sun's surface. They release radiation and charged particles that can interfere with satellites, power grids, and communication systems on Earth. When a solar flare happens, astronomers observe it 8 minutes and 20 seconds after it actually occurred. By the time we see the flare, it's already ancient history. The radiation has already been traveling toward Earth for 8 minutes. If it's going to cause problems, those problems are already on their way. There's no warning period built into the observation. The warning is the observation. The same principle applies to everything about the sun. Its rotation, its sunspots, the churning convection on its surface. All of it delayed by 8 minutes and 20 seconds. We can never observe the sun in real time. We can only ever see what it was doing 8 minutes ago. 8 minutes feels manageable to our minds. We can hold that span of time in our thoughts. We experience 8-minute intervals regularly, waiting for water to boil, standing in line, sitting through a commercial break. 8 minutes is within the range of normal human patience. But here's what makes it unsettling. 8 minutes of light travel time represents 150 million kilometers of empty space. That's the gap between us and the sun. And light, moving at the fastest possible speed, takes 8 full minutes to cross it. If you tried to drive to the sun at highway speed, let's say 100 kilometers per hour, it would take you about 170 years. If you flew on a commercial airliner at cruising speed, maybe 900 kilometers per hour, it would still take nearly 19 years of continuous flight. The fastest spacecraft we've ever built, the Parker Solar Probe, which is specifically designed to approach the sun, travels at roughly 190 kilometers per second at its top speed. Even at that incredible velocity, it takes months to reach the sun's vicinity. And yet, Light makes the journey in 8 minutes and 20 seconds. This is the first distance where light travel time starts to feel significant. The moon's 1 second delay is noticeable but brief. 8 minutes is something else. 8 minutes is a meaningful chunk of time. It's long enough to make you aware of the gap, long enough to change how you think about the sun. The sun isn't here with us. It's over there, separated by a gulf that light takes 8 minutes to cross. We live in its warmth, but that warmth is ancient by the time it reaches us. We see its light, but that light is a recording of the past, not a live feed of the present. And the sun is close. Cosmically speaking, it's right next door. It's part of our immediate neighborhood. We orbit it. We're gravitationally bound to it. It's the center of our solar system, the anchor around which everything else revolves. 8 minutes feels manageable. It's a coffee break, a brief pause in the day. But this is where our intuition begins to fail us, because beyond the sun, even minutes become inadequate. Beyond the sun, the solar system stretches outward into deepening cold and darkness. The planets occupy orbits measured not in minutes, but in hours of light travel time. And at these distances, communication with spacecraft becomes an exercise in patience. Jupiter, the largest planet in our solar system, orbits at varying distances from Earth, depending on where both planets are in their respective paths around the Sun. At its closest approach, Jupiter sits roughly 43 light minutes away. At its farthest, that distance extends to nearly 50 light minutes. Let's use a middle figure. About 43 minutes for light to travel from Earth to Jupiter. 43 minutes, that's less than an hour. It's a typical lunch break. A single episode of a television show. It doesn't feel like an insurmountable span of time, but consider what it means for communication. When the Juno spacecraft orbits Jupiter, every command sent from Earth takes 43 minutes to arrive. If Juno encounters a problem, if its instruments malfunction or its trajectory needs adjustment, mission controllers on Earth won't know for 43 minutes. And then, any corrective command they send takes another 43 minutes to reach the spacecraft. That's an hour and 26 minutes round trip. Nearly an hour and a half between problem and solution. This is why spacecraft operating in the outer solar system must be highly autonomous. They can't rely on real-time human guidance. The distances are too great. Light is too slow. By the time information travels back and forth, the moment has passed. Saturn sits even farther out, roughly 80 light minutes from Earth depending on orbital positions. That's 1 hour and 20 minutes for light to make the one-way journey. The Cassini spacecraft, which orbited Saturn for 13 years before its mission ended, operated under this communication delay for its entire operational life. Every image it captured, every measurement it took, every piece of data it collected, took 80 minutes to reach Earth after being transmitted. When Cassini made its final plunge into Saturn's atmosphere, the event had already happened by the time mission controllers received the signal. The spacecraft was gone, vaporized in Saturn's upper atmosphere, more than an hour before anyone on Earth knew it. The farewell signal was a ghost, a transmission from a spacecraft that no longer existed, light, carrying news of a death that had already occurred. Uranus lies roughly 2.5 light hours from the Sun. 2.5 hours. That's an entire afternoon. a full movie and then some. Light leaving Uranus takes 2.5 hours to reach Earth. A round-trip communication delay would be 5 hours, nearly half a working day. Voyager 2, the only spacecraft to visit Uranus, flew past in 1986. Every command sent to the spacecraft during that encounter was sent hours in advance, timed to arrive exactly when needed. There was no possibility of real-time control. The spacecraft had to execute its observation sequence autonomously, following pre-programmed instructions because light was simply too slow to allow for human intervention. And then there's Neptune, the most distant of the traditional planets, over 4 light hours away. 4 hours and 10 minutes more precisely, though the distance varies with orbital mechanics. 4 hours for light to travel from Neptune to Earth. 4 hours back if you're sending a signal the other way. An 8-hour round-trip delay. 8 hours. A full night's sleep. An entire workday. If you sent a message to Neptune in the morning, you wouldn't receive a response until late afternoon, even if that response was sent immediately upon receipt. Which it wouldn't be because there's no one on Neptune to send it. But if there were, that's the delay you'd face. Voyager 2 reached Neptune in 1989. The encounter lasted only a few hours, but every moment of it had to be planned with exquisite precision. There was no way to adjust course or change instructions on the fly. The spacecraft was on its own, 4 light hours from home, operating according to commands sent half a day earlier. These are our neighboring planets. These are the worlds within our own solar system, orbiting the same star we do, held in the same gravitational family. And yet, they are separated from us by hours of light travel time. Hours, not seconds, not minutes, but hours. The kind of time you notice, the kind of time that defines your day. The edge of our solar system, if we define it by the heliopause, the boundary where the influence of the sun gives way to interstellar space, sits roughly 11 light hours away. Voyager 1, humanity's most distant spacecraft, crossed that boundary in 2012. It's now traveling through interstellar space more than 22 light hours from Earth. Any signal it sends takes nearly a full day to reach us. 22 hours and change. Almost an entire rotation of our planet. When Voyager 1 transmits data, that data is already a day old by the time we receive it. The spacecraft could have experienced a malfunction, a collision with interstellar dust, a power failure, and we wouldn't know for nearly a day. And if we wanted to send a command in response, that command would take another full day to arrive. 2 days round trip, 48 hours between question and answer. This is our solar system. This is our immediate cosmic neighborhood, the region of space we've actually explored with physical machines. And it's measured in hours. 4 hours, 8 hours, 22 hours. Half a day of light travel just to reach the edge. 4 hours. That's how long light takes to reach Neptune. A short work shift. Half a sleep cycle. And yet we're still in our own cosmic backyard, barely beyond our front door. At some point in the 17th century, astronomers realized they had a problem. The universe was larger than anyone had imagined. Telescopes were revealing stars scattered across distances that defied comprehension. And the standard units of measurement, kilometers and miles, had become useless. You can say that something is 1 trillion kilometers away. You can write the number down. You can do the mathematics. but the number itself conveys nothing meaningful to the human mind. 1,000,000,000,000 is too large. It's abstract. It doesn't connect to anything in your lived experience. Your brain can't hold it, can't visualize it, can't relate it to the world you know. So astronomers did something clever. They stopped measuring distance in units of space and started measuring it in units of time. Specifically, they measured how long it takes light to cross a given distance. This wasn't about travel time for a spacecraft or a person. It was about light itself, moving at the fastest possible speed in the universe. And from this approach, the light year was born. A light year is the distance that light travels in one Earth year. That's it. Simple definition. But the implications are enormous. Let's work through the calculation. Light travels at roughly 300,000 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year, give or take, depending on whether it's a leap year. Multiply all those numbers together and you get the distance light covers in 1 year. The result is approximately 9,460,000,000,000 kilometers, nearly 9.5 trillion kilometers. That's 1 light year. To put that in perspective, remember that the Moon is roughly 384,000 kilometers away. 1 light year is about 24 billion times farther than the Moon. The Sun, at 150 million kilometers, is closer. But even the Sun's distance fits into a light year more than 63,000 times. A light year isn't just big, it's incomprehensibly big. It's the kind of distance that breaks your intuition. You can't picture it. You can't relate it to anything familiar. The numbers are too large, the scale too vast. And yet, astronomers use light years constantly because they are the only unit that makes sense when dealing with the cosmos. Kilometers and miles fail. They produce numbers with so many zeros that they become meaningless. But light years, strange as they are, at least give you a framework. They tell you how long light, moving at the universe's speed limit, takes to cover the distance. This is a critical shift in thinking. A light year isn't really about light. It's about distance. But by framing that distance in terms of time, in terms of how long light takes to travel it, the unit becomes slightly more graspable. Not fully graspable, not visualizable in any true sense, but graspable enough that you can use it, work with it, build a mental model around it. The invention of the light year wasn't arbitrary. It emerged from necessity. As telescopes improved and stars revealed themselves in greater numbers and at greater distances, astronomers needed a way to communicate those distances without drowning in zeros. The light year provided that solution. It also unified 2 concepts that seem separate in everyday life: distance and time. On Earth, you can measure distance without thinking about time. A road is 10 kilometers long whether you walk it or drive it. The distance is fixed. Time varies depending on your speed. But in astronomy, distance and time are inseparable. The distance to a star is also the age of the light you're seeing from that star. A star 10 light years away is a star whose light has been traveling for 10 years to reach you. This means that every astronomical observation is simultaneously an observation of space and time. You're not just looking out into the universe, you're looking back into the past. The farther away something is, measured in light years, the older the light, and the deeper into history you're peering. This is why the light year matters. It's not just a unit of measurement, it's a conceptual tool that helps you understand the nature of cosmic observation. Distance equals time. Space equals history. The two are bound together by the speed of light, which is the one constant, the one unchanging factor in all of this. The light year also reveals something humbling. 9.5 trillion kilometers is the distance light travels in a single year. And light is fast. It's the fastest thing in existence. Nothing can move quicker. And yet, 1 year of light travel gets you only so far. In cosmic terms, a light year is a small distance, a modest hop. The universe is measured in millions and billions of light years, scales that dwarf even this enormous unit. But we'll get to that. For now, the important point is this. The light year exists because normal units of distance fail at cosmic scales. Kilometers and miles produce numbers too large for the human mind to process. Light years convert those incomprehensible distances into something slightly more manageable. Not easy to understand, not intuitive, but workable. 9 trillion kilometers. Your mind can process the words, but it cannot truly grasp the distance. No human mind can. And that's before we venture to the nearest star. Proxima Centauri is the nearest star to our Sun. Not the nearest star system, the nearest individual star. It's part of a triple star system called Alpha Centauri, but Proxima itself is the closest of the three. And it sits 4.24 light-years away from us. 4.24 light-years. Let's round to 4.25. That's the distance. That's how far light, traveling at maximum speed, takes to cross the void between our Sun and the next nearest star. 4.25 years. Think about what that means. A photon leaves the surface of Proxima Centauri and begins traveling toward Earth. It moves through empty space at 300,000 kilometers per second. It doesn't slow down. It doesn't speed up. It just moves constantly at the maximum speed the universe allows. And it takes 4.25 years to arrive. 4.25 years ago, you were living a different life. Maybe slightly different, maybe dramatically different, but different nonetheless. The world was in a different state. Events that are now history were still in the future, and a photon that left Proxima Centauri back then is only just now reaching Earth. When you look at Proxima Centauri through a telescope, you're not seeing it as it is today. You're seeing it as it was 4.25 years ago. The star could have changed. It could have flared, it could have dimmed, it could, theoretically, have exploded, though that's not how red dwarf stars typically behave. But whatever has happened in the last 4 years, you don't know yet. You won't know until the light from those events reaches Earth. This is the reality of interstellar distance. Even our nearest neighbor is separated from us by more than 4 years of light travel. 4 years of empty space, 4 years of void, and there's no way around it. No shortcut, no faster route. Light is already taking the fastest possible path, and it still needs 4.25 years to make the journey. Now consider what this means for human space travel. If we wanted to send a spacecraft to Proxima Centauri, and if that spacecraft could somehow travel at the speed of light, which is physically impossible for anything with mass, The journey would take 4¼ years, one way. The spacecraft would arrive 4¼ years after launch. If it sent a signal back to Earth immediately upon arrival, that signal would take another 4¼ years to reach us. 8½ years total for a round-trip message. But we can't travel at the speed of light, not even close. The fastest spacecraft humanity has ever built is Voyager 1, currently traveling at roughly 17 kilometers per second. That sounds fast. It is fast by any terrestrial standard, but it's a tiny fraction of light speed. Light travels at 300,000 kilometers per second. Voyager moves at 17 kilometers per second. That's about 0.006% of light speed. At that velocity, Voyager 1 would take more than 70,000 years to reach Proxima Centauri. 70,000 years. Longer than recorded human history. Longer than human civilization has existed. Longer than our species has been using agriculture or building cities or writing down our thoughts. Even if we could build a spacecraft that traveled at 10% of light speed, which would require propulsion technology far beyond anything we currently possess, the journey to Proxima Centauri would still take 42½ years. That's longer than most careers, longer than many human lifespans in much of the world. A person born at the launch of such a mission would be middle-aged by the time it arrived. And Proxima Centauri is the closest star, the very nearest one. After Proxima, the next nearest stars are even farther. The distances only grow from here. Proxima Centauri has planets, at least 2, possibly more. One of them, Proxima Centauri b, orbits within the star's habitable zone. This is the region where liquid water could theoretically exist on a planet's surface. This planet has been the subject of immense interest since its discovery. Could it harbor life? Could it have an atmosphere? Could it, in any way, resemble Earth? We don't know. We can observe the planet only through indirect methods. We see the slight wobble it causes in its star's motion. We measure the tiny dip in starlight when the planet passes in front of Proxima Centauri from our perspective. But we can't see the planet directly. We can't study its surface. We can't analyze its atmosphere in detail. Not yet. And even if we could, everything we observe would be 4¼ years out of date. If something happened on Proxima Centauri b today, we wouldn't see it until 4¼ years from now. If life exists on that planet, and if that life were somehow sending signals into space, those signals would take more than 4 years to reach us. And if we responded, our response would take another 4 years to arrive. This is the permanence of cosmic isolation at interstellar distances. Even at our closest neighboring star, communication is measured in years. Round-trip messages take nearly a decade. Travel, even at wildly optimistic speeds, would take decades at minimum. With any realistic technology, it would likely take centuries or millennia. 4 light years is the closest star beyond our Sun. 4 years at the fastest speed the universe allows. And our galaxy contains hundreds of billions of stars, scattered across distances that make this seem trivial. The Milky Way is our home galaxy. It's the vast structure of stars, gas, dust, and dark matter that contains our solar system, our sun, and everything we can see in the night sky without a telescope. And it's enormous in ways that dwarf everything we've discussed so far. The Milky Way is roughly 100,000 light-years across. From one edge to the other, If you could somehow travel at the speed of light, the journey would take 100,000 years, 100 millennia, 1,000 centuries. Longer than modern humans have existed as a species. Let that settle in your mind for a moment. 100,000 years for light to cross our galaxy. Light moving at the maximum possible speed at 300,000 kilometers per second would need 100,000 years to travel from one side of the Milky Way to the other. Our Sun sits about 26,000 light years from the galactic center. We're not at the edge, but we're not at the center either. We're out in one of the spiral arms in a relatively quiet neighborhood, orbiting the galactic core at a leisurely pace. It takes our solar system roughly 230 million years to complete one full orbit around the galaxy. The last time we were in this position, dinosaurs were just beginning to diversify on Earth. 26,000 light years to the center. That means the light we see from the galactic core left that region 26,000 years ago. When that light began its journey, humans were still living in the Stone Age. We were hunter-gatherers. We hadn't invented agriculture. We hadn't built cities. We hadn't developed writing. And yet, light from the center of our own galaxy was already traveling toward Earth, moving through space at maximum speed, and it's only just now arriving. The galactic center is home to a supermassive black hole called Sagittarius A star. This black hole contains roughly 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. It's an object of immense gravitational power, and it sits at the heart of our galaxy, anchoring everything around it. We observe Sagittarius A star through radio telescopes and infrared imaging. We watch stars orbit around it, moving at tremendous speeds, tracing elliptical paths that reveal the black hole's presence, even though we can't see the black hole itself. But everything we observe is 26,000 years old. Every image, every measurement, every data point. It all comes from light that left the galactic center when humans were fashioning stone tools and living in caves. If something dramatic happened at the galactic center today, if the black hole consumed a star, or if a massive burst of radiation erupted from the surrounding accretion disk, we wouldn't know for 26,000 years. The event would be over. Ancient history, lost to time, and we'd still be seeing the galaxy as it was before it happened. The Milky Way has structure. It's not a uniform distribution of stars. It's organized into a disk with spiral arms extending outward from the central bulge. These spiral arms are regions of higher stellar density, places where stars are more tightly packed, where gas clouds are collapsing to form new stars, where the galaxy's ongoing cycle of birth and death plays out. Our solar system resides in a spiral arm called the Orion Arm. Sometimes it is known as the Orion Spur. It is a minor arm, not one of the major spiral structures, but it is our local neighborhood. The stars you see at night are all part of this region. The constellations you recognize are all part of this region. They are our neighbors, relatively speaking, though many of them are still dozens of light years away. Some are hundreds of light years away. The Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is uncertain. Many stars are hidden behind dust clouds. Others are simply too faint to detect. But the order of magnitude is clear. Hundreds of billions. each one a sun in its own right, each one potentially hosting planets, each one separated from its neighbors by light years of empty space. All of these stars are spread across 100,000 light years. All of this structure is spread across 100,000 light years. All of this immense complexity is spread across 100,000 light years. The galaxy we observe is a patchwork of different time periods. It is stitched together by the varying distances light has traveled to reach us. Stars closer to us appear as they were recently, perhaps decades ago, perhaps centuries ago. Stars on the far side of the galaxy appear as they were tens of thousands of years ago. We are seeing different eras of galactic history simultaneously, all layered on top of each other, creating a composite image that does not actually represent any single moment in time. This is what happens when distances are measured in light years. Time becomes part of the picture. You cannot separate observation from history. Every glance at the night sky is a glance backward through time. The depth of that backward glance depends on how far the light has traveled. 100,000 light years from edge to edge, 26,000 light years to the center. These distances are so large that they make interstellar travel seem utterly impossible. Interstellar travel is already difficult at the scale of a few light years. Even if you could travel at the speed of light, crossing the galaxy would consume 100,000 years. 100,000 years of subjective time for observers back home. For the travelers themselves, relativistic effects would compress that time significantly. But for everyone else, it would be a journey into the deep future. For the civilization that launched the mission, it would be a journey into the deep future. 100,000 years for light to cross our galaxy. 100 millennia. Longer than our species has used language. And this is just one galaxy among hundreds of billions. Beyond the Milky Way, space opens into an even larger scale. The next major structure is the Andromeda Galaxy, our nearest large galactic neighbor. It's the most distant object you can see with your naked eye on a clear, dark night. A faint smudge in the constellation Andromeda. A soft glow that doesn't look like much until you realize what it represents. Andromeda sits 2.5 million light years away from us. 2.5 million light years. 2.5 million years of light travel. The light you see when you look at Andromeda left that galaxy 2.5 million years ago. This was during the Pliocene epoch on Earth. Early human ancestors were just beginning to emerge. Homo habilis, one of the first members of our genus, was using simple stone tools. Modern humans wouldn't exist for another 2 million years. That's how old the light from Andromeda is by the time it reaches your eyes. You're not seeing Andromeda as it is now. You're seeing it as it was when our ancestors were barely recognizable as human. Everything that has happened in Andromeda over the last 2.5 million years is invisible to us. We won't see those events until their light completes the journey across intergalactic space. Andromeda is a spiral galaxy. Much like the Milky Way, it's slightly larger than our galaxy. It contains roughly 1 trillion stars compared to our few 100 billion. It has its own spiral arms, its own central bulge, its own supermassive black hole at the core, and it's heading toward us. The Milky Way and Andromeda are on a collision course. They're being pulled together by mutual gravitational attraction, slowly closing the gap between them. In roughly 4.5 billion years, the two galaxies will merge. They will create a larger elliptical galaxy that astronomers have already nicknamed Milkomeda. But that collision is so far in the future that it's almost abstract. Our sun will be nearing the end of its life by then. Earth may no longer be habitable. Humanity, if it still exists, will be unrecognizably different. The Milky Way and Andromeda are part of a larger structure called the Local Group. This is a collection of more than 50 galaxies bound together by gravity. It occupies a region of space roughly 10 million light-years across. 10 million light-years. The number keeps growing. The scale keeps expanding, and yet, in cosmic terms, the Local Group is a small structure, a modest cluster, a neighborhood. Most of the galaxies in the Local Group are dwarf galaxies. These are small collections of stars that orbit the larger galaxies like satellites. The Milky Way has dozens of these dwarf companions. The Large Magellanic Cloud and the Small Magellanic Cloud are two of the most prominent. They are visible from the southern hemisphere as faint clouds in the night sky. These are small galaxies containing only billions of stars rather than hundreds of billions. They orbit the Milky Way at distances of roughly 160,000 and 200,000 light-years respectively. The Triangulum Galaxy, also known as Messier 33, is the third largest member of the Local Group. This is after Andromeda and the Milky Way. It sits about 3 million light-years away, a bit farther than Andromeda. The light from Triangulum that reaches us tonight left that galaxy 3 million years ago. This was when early hominids were just beginning to diverge from other apes. 3 million years. The span of time feels almost geological. It is longer than human history, longer than human civilization, longer than humans have existed in anything resembling our current form. And that is just the light travel time to a neighboring galaxy within our Local Group. At these distances, galaxies themselves become the primary unit of structure. Individual stars do not matter much. You cannot resolve individual stars in Andromeda with the naked eye. Even with telescopes, only the brightest stars in Andromeda are visible as distinct points of light. Most of what you see is the combined glow of billions of stars blurred together into a diffuse haze. Galaxies at these distances reveal their overall structure. You can see spiral arms. You can identify regions of active star formation, bright patches where massive young stars are being born. You can observe the galactic nucleus, the bright core where stars are densely packed. But the individual details are lost. The specific stars and planetary systems and the small-scale features are lost. The distances are too great. The light has traveled too far. This is where observation starts to shift from the study of stars to the study of galaxies as whole entities. Astronomers talk about galactic morphology, the shapes and structures of galaxies. Spiral, elliptical, irregular. They measure galactic rotation, the speed at which galaxies spin around their centers. They study galactic interactions, the ways galaxies influence each other through gravity, sometimes merging, sometimes passing by and distorting each other's shapes. And all of this is seen through the lens of time. The Andromeda galaxy you observe tonight is the Andromeda galaxy of 2.5 million years ago. The Triangulum galaxy is 3 million years in the past. Every observation is historical. Every measurement is ancient. The present state of these galaxies is unknowable to us. We can only see what they were, not what they are. The local group spans 10 million light years. That is the breadth of our immediate cosmic neighborhood. And within that span, light takes millions of years to travel from one galaxy to another. Communication between galaxies, if such a thing were possible, would require waiting millions of years for a response. A round-trip message to Andromeda would take 5 million years. 2.5 million years. That is not just distance. It is a time machine showing us the universe as it was when the first humans walked the African savanna. And we are only just leaving our local neighborhood. The universe extends far beyond the local group, far beyond anything we've discussed so far. And at some point, when you look deep enough into space, you encounter a boundary. Not a physical edge, not a wall or a barrier, but a horizon defined by time itself. The observable universe is the sphere of space from which light has had time to reach us since the beginning of the universe. It's approximately 93 billion light-years in diameter, 46.5 billion light-years in any direction from Earth. That's the radius of the observable universe, the cosmic horizon. 93 billion light-years across. The number is so large it ceases to mean anything in conventional terms. You can't relate it to human experience. You can't visualize it. You can barely conceptualize it. But it's the size of everything we can see, everything that's observable, everything that's accessible to our telescopes and instruments. Here's where things get strange. The universe is approximately 13.8 billion years old. It began with the Big Bang 13.8 billion years ago. You might think then that the most distant objects we can see would be 13.8 billion light-years away. Light has had 13.8 billion years to travel. So the farthest light should come from objects 13.8 billion light-years distant. But that's not how it works. The observable universe is much larger than 13.8 billion light-years across. It's 93 billion light-years. The reason for this discrepancy is cosmic expansion. Space itself has been expanding since the Big Bang. And as space expands, it carries galaxies with it, stretching the distances between them. When a photon left a distant galaxy 13.8 billion years ago, that galaxy was much closer than it is now. The photon traveled through space toward us. But while it was traveling, space itself was expanding, increasing the distance between us and the galaxy. By the time the photon reaches us, the galaxy it came from has moved much farther away due to the expansion of space. This means that an object whose light has been traveling for 13.8 billion years is now located roughly 46.5 billion light-years away. The light travel distance and the actual current distance are two different things. The light travel distance tells you how long the light has been traveling. The actual distance tells you where the object is now, accounting for the expansion of space. The edge of the observable universe is defined by the cosmic microwave background. This is the oldest light we can see, the afterglow of the Big Bang itself. It comes from a time roughly 380,000 years after the Big Bang. This was when the universe cooled enough for atoms to form and light to travel freely through space. Before that moment, the universe was opaque, a hot plasma that scattered light in all directions. After that moment, light could travel unimpeded. And some of that light has been traveling toward us ever since. The cosmic microwave background represents a sphere around us, roughly 13.8 billion light-years away in light travel time, but roughly 46.5 billion light-years away in actual current distance. It's the farthest we can see. Beyond that, there's no light to observe. Not because there's nothing there, but because light from anything farther hasn't had time to reach us yet. And beyond the cosmic horizon, the universe continues. We just cannot see it. We have no way to observe it. The light from those regions has not reached us. Depending on the rate of cosmic expansion, some of that light may never reach us. There are parts of the universe that are receding from us faster than the speed of light, due to the expansion of space. We will never be able to see them, no matter how long we wait. This is the cosmic horizon, a boundary imposed not by physics in the traditional sense, but by time and expansion. Light travels at a finite speed. The universe has existed for a finite amount of time, so there is a limit to how far light can have traveled, and that limit defines what we can observe: 93 billion light-years. That is the diameter of everything we can see. Every galaxy, every star, every photon that has reached us since the beginning of time. It all exists within this sphere. And outside this sphere, there is more universe. Possibly infinitely more, we just cannot see it. The observable universe contains an estimated 2 trillion galaxies. That is 2 million galaxies, each one containing billions or trillions of stars, each one spread across thousands or hundreds of thousands of light years. And all of them are scattered across 93 billion light-years of space. When you observe a galaxy 10 billion light-years away, you are seeing it as it was 10 billion years ago. The universe was younger then. Stars were forming at higher rates. The chemical composition of galaxies was different. The structures we see today, the galaxy clusters and superclusters, were still forming. You are witnessing an earlier chapter in cosmic history. When you observe the cosmic microwave background, you are seeing the universe as it was just 380,000 years after the Big Bang. You are looking at the earliest moment visible to us, the universe in its infancy, hot, dense, filled with hydrogen and helium, but no stars yet, no galaxies, no structure, just the raw material that would eventually coalesce into everything we see today. 93 billion light-years across, and that is just what we can see. The sphere of space from which light has had time to reach us since the Big Bang. Beyond that edge, the universe continues, perhaps forever. There is no universal now in the cosmos. No single moment that exists simultaneously everywhere. The concept of now breaks down when you are dealing with distances measured in light years. Time and simultaneity become relative, dependent on location and the speed of light. When you look at a star 100 light years away, you see it as it was 100 years ago. The light reaching your eyes tonight left that star a century ago. That was when your great-grandparents might have been children. That was when the world was fundamentally different. That star, as it exists right now in this present moment, is invisible to you. You will not see its current state for another 100 years, when the light from this moment finally completes its journey. Now imagine a civilization on a planet orbiting that star. Imagine they have telescopes. Imagine they are looking back at Earth. What do they see? They see Earth as it was 100 years ago. They see the early 20th century. They see a planet in the middle of industrialization, before spaceflight, before computers, before most of the technology that defines our current era. If they are watching closely, they might see the lights of cities. They might see the signs of a technological civilization. But they are seeing our past, not our present. This creates a strange asymmetry. We see them 100 years ago. They see us 100 years ago. But neither of us sees the other as they currently are. There is a 200-year gap between observation and reality. Our now and their now are separated by the time it takes light to travel between our worlds. And if we tried to communicate, the delay would be profound. If we sent a message today, a radio signal or a laser beam, it would travel at the speed of light and take 100 years to reach them. If they responded immediately, their response would take another 100 years to come back. 200 years for a round-trip message. 4 human lifetimes. The person who sent the original message would be long dead before any reply arrived. Their great-great-grandchildren might be the ones to receive it. This is what Einstein's theory of relativity tells us. There is no absolute simultaneity across large distances. Events that seem simultaneous to one observer are not simultaneous to another observer in a different location or moving at a different speed. And when distances are measured in light years, this effect becomes impossible to ignore. The star Betelgeuse in the constellation Orion sits roughly 550 light-years from Earth. It is a red supergiant, a massive star nearing the end of its life. Astronomers expect it to explode as a supernova sometime in the next 100,000 years, though the exact timing is uncertain. When it does explode, it will be one of the brightest objects in the sky, visible even during the day. But here is the thing. Betelgeuse might have already exploded. The explosion might have happened centuries ago, and we would not know. The light from that explosion is still traveling toward us, moving through space at 300,000 kilometers per second. It will not arrive until it arrives. If Betelgeuse exploded 200 years ago, the light from that event is still 350 years away from reaching Earth. The explosion has happened, but we exist in a version of the universe where it has not happened yet, because the information has not reached us. From our perspective, Betelgeuse still exists. It is still visible in the night sky. It is still a red supergiant. And it will remain so until the light from its destruction finally arrives. Only then will we know. Only then will the explosion become part of our observable reality. This is the nature of light travel time. It creates a buffer between event and observation. Cause and effect are separated not just by space, but by time. The farther away something is, the larger that buffer becomes. At 10,000 light years, you are seeing events from 10,000 years ago. The rise of agriculture on Earth, the first permanent human settlements, the invention of writing still thousands of years in the future. If a star went supernova 10,000 light-years away during the time of early human civilization, the light from that explosion is only now reaching us. At 1 million light-years, you are seeing events from 1 million years ago. Early humans were still evolving in Africa. Homo erectus was spreading across continents. Modern humans would not exist for hundreds of thousands of years. At 1 billion light-years, you are looking at a version of the universe from 1 billion years ago. Earth was vastly different. Multicellular life was still relatively new. The continents were arranged differently. The atmosphere had less oxygen. Nothing resembling modern ecosystems existed yet. Every photon carries this historical information. Every telescope is, in essence, a time machine. When astronomers look at distant galaxies, they are not studying the current state of those galaxies. They are studying their past. And the farther they look, the deeper into history they peer. This has profound implications for understanding the universe. It means we can directly observe cosmic history. We can watch galaxies forming in the early universe. We can see stars being born in conditions that no longer exist in nearby space. We can study the evolution of large-scale structure over billions of years simply by looking at objects at different distances. But it also means there is a fundamental limit to what we can know about the present state of the universe. We can see the past, we can observe history. But the current state of anything beyond our immediate neighborhood is hidden from us, locked behind the light travel time. The universe has a now, presumably, but we cannot access it. We can only access the past, spread out across space in layers of increasing age. The universe you see is a patchwork of different moments in time, stitched together by the speed of light. And this creates a peculiar effect. The farther you look, the younger the cosmos becomes. Telescopes are time machines. Not in the science fiction sense, they don't transport you backward through time, but they allow you to see the past directly. Every photon that enters a telescope has been traveling for a specific amount of time. That time corresponds to a specific era in cosmic history. When you point a telescope at a galaxy 1 billion light-years away, you're observing that galaxy as it existed 1 billion years ago. You're seeing the stars that were shining then, the structure that existed then, the conditions that prevailed then. The galaxy has changed since that light left. Stars have been born, stars have died. The spiral arms have rotated. The overall structure has evolved. But you see none of that. You see only what was. This makes astronomy fundamentally different from most sciences. A biologist studying an organism is studying it in its current state. A chemist analyzing a reaction is observing it as it happens. But an astronomer is always observing history. There's no way to see the present state of anything beyond our solar system. The light travel time creates an unavoidable delay. The Hubble Space Telescope has captured images of galaxies more than 13 billion light-years away. These are some of the most distant objects ever observed. The light from these galaxies has been traveling for more than 13 billion years. It left when the universe was young, less than 1 billion years old. These are early galaxies, among the first generations of galaxies to form after the Big Bang. They don't look like modern galaxies. They're smaller, less structured, more irregular in shape. They're actively forming stars at rates far higher than what we see in nearby galaxies today. The universe was different back then. Denser, hotter, more chaotic. And we can see that difference directly because we're looking at ancient light. The Hubble Deep Field images are particularly striking. These are photographs of tiny patches of apparently empty sky. Regions where no bright stars or nearby galaxies are visible to the naked eye, or even to modest telescopes. But when Hubble stared at these patches for days, accumulating light over long exposures, thousands of galaxies appeared. Faint smudges, distant collections of stars, some of them over 10 billion light-years away. Each of those galaxies represents a snapshot of a different moment in cosmic history. The closer ones, a few billion light-years away, show galaxies that look relatively modern. Spiral structures are evident. Star formation rates are modest. They resemble the Milky Way or Andromeda in many ways. But the farther ones, the galaxies over 10 billion light-years distant, look different. They're smaller, more compact, less organized. They're younger versions of what galaxies would eventually become. This is how astronomers study galactic evolution. They don't watch a single galaxy change over time. That would require billions of years of observation, far longer than human civilization has existed. Instead, they observe many galaxies at different distances, and therefore at different ages, and piece together a timeline. Galaxies 10 billion light-years away show what galaxies looked like 10 billion years ago. Galaxies 5 billion light-years away show what galaxies looked like 5 billion years ago. Nearby galaxies show what galaxies look like in the relatively recent past, a few million or tens of millions of years ago. The James Webb Space Telescope, launched in late 2021, can see even farther than Hubble. It observes in infrared wavelengths, which allows it to detect light from extremely distant galaxies. These are galaxies whose visible light has been redshifted into the infrared due to cosmic expansion. Webb has captured images of galaxies that existed less than 500 million years after the Big Bang. These are among the earliest galaxies ever observed. They were forming in an era when the universe was still emerging from its dark ages, when the first stars were igniting, and when the first large-scale structures were taking shape. These galaxies are incredibly faint. Their light has been traveling for over 13 billion years. It has been dimmed by distance and redshift. But they're there, visible in Webb's deep images. They provide direct evidence of what the early universe looked like. Not models, not simulations. Actual photographs of ancient galaxies as they appeared in the first billion years of cosmic history. At 2 billion light-years, galaxies look fairly modern. Star formation continues, but at a measured pace. Large spiral galaxies are common. Galactic clusters have formed. The universe resembles, in broad strokes, what we see nearby. At 5 billion light-years, galaxies are more active. Star formation rates are higher. Galactic mergers are more common. The universe is denser, with galaxies packed more closely together. Interactions between galaxies are frequent. These interactions trigger bursts of star formation. They reshape galactic structures. At 10 billion light-years, galaxies are smaller and more chaotic. Many are irregularly shaped. Massive elliptical galaxies are rare. The large, well-organized spiral galaxies we see today are still forming. The universe is younger, more energetic, more violent in its processes. At 13 billion light-years, we're seeing the universe in its infancy. Galaxies are just beginning to form. They're small collections of stars, often no larger than dwarf galaxies by today's standards. The intergalactic medium is different. It is filled with neutral hydrogen that hasn't yet been ionized by starlight. The cosmic web is still taking shape. This is the large-scale structure of filaments and voids that characterizes the modern universe. This is the power of light travel time. It turns distance into history. The farther you look, the farther back you see. Every telescope image is an archaeological record. It preserves moments from different epochs in the universe's past. By observing objects at many different distances, astronomers can reconstruct the story. They can see how the universe has evolved over billions of years. Every photon carries history. Every telescope is an archaeological instrument. It excavates not Earth, but time itself. And the deeper we look, the stranger the universe becomes. Interstellar travel, in any practical sense, is impossible. Not difficult, not challenging. Impossible. This is true given our current understanding of physics and our current technological capabilities. The distances are too vast. The speeds required are too great, and the energy needed exceeds anything we can produce. Consider our fastest spacecraft. Voyager 1 was launched in 1977. It is currently traveling at about 17 kilometers per second relative to the Sun. That is roughly 61,000 kilometers per hour. Fast by any terrestrial standard. Faster than anything humans regularly experience. But in cosmic terms, it is incredibly slow. Light travels at 300,000 kilometers per second. Voyager 1 travels at 17 kilometers per second. That means Voyager is moving at roughly 0.006% of the speed of light. Not 6%, not 0.6%, 0.006%. A tiny fraction. At that speed, Voyager 1 would take more than 70,000 years to reach Proxima Centauri. Proxima Centauri is the nearest star beyond our Sun. 70,000 years. That is longer than human civilization has existed, longer than we have had agriculture, cities, writing, or any form of recorded history. If Voyager had been launched 70,000 years ago by Neanderthals or early Homo sapiens, it would only now be arriving at Proxima Centauri. And Voyager 1 was not designed for interstellar travel. It was designed to study the outer planets. Its speed is a consequence of gravitational assists from Jupiter and Saturn. It was not a deliberate attempt to achieve interstellar velocity. We have never built a spacecraft specifically intended to reach another star. The engineering challenges are insurmountable with current technology. Let us imagine for a moment that we could build a spacecraft capable of traveling at 10% of the speed of light. This would require propulsion technology far beyond anything we currently possess. Nuclear pulse propulsion, antimatter engines, laser-driven light sails, something exotic and powerful. But let us assume it is possible. At 10% of light speed, the journey to Proxima Centauri would take roughly 42 years. 42 years. A human lifetime or close to it. A person born at the launch of such a mission might be middle-aged by the time it arrived. Assuming they lived that long, assuming the spacecraft functioned perfectly for 4 decades. assuming nothing went wrong during the journey through interstellar space. And that is to the nearest star. The next nearest stars are farther. Sirius is the brightest star in the night sky. It is 8.6 light years away. At 10% of light speed, 86 years to arrive. Vega is another prominent star. It is 25 light years distant, 250 years at 10% of light speed. Longer than the United States has existed as a nation, but 10% of light speed is wildly optimistic. It is not clear we could ever achieve that velocity with a crewed spacecraft. The energy requirements are staggering. The engineering challenges immense. And even if we could, the journey times remain prohibitive for anything resembling traditional space travel. Some proposals involve generation ships, spacecraft large enough to support a self-sustaining human population for centuries or millennia. The people who launched the mission would die en route. Their children would be born on the ship. Their grandchildren would grow up never having seen Earth. And eventually, many generations later, their distant descendants would arrive at the destination. These descendants would be born in space. They would live their entire lives in space. And they would know Earth only through historical records and cultural memory. The psychological and social challenges of such a mission are difficult to imagine. How do you maintain a stable society aboard a spacecraft for hundreds or thousands of years? How do you preserve knowledge and culture across generations? How do you ensure the mission continues when everyone involved knows they will never see the destination? And then there is the problem of relativistic speeds. If you somehow accelerated a spacecraft to a significant fraction of light speed, say 50% or 70%, relativistic effects would become important. Time dilation would occur. Time would pass more slowly for the travelers relative to people back on Earth. A journey that takes 100 years from Earth's perspective might take only 50 years from the traveler's perspective, depending on the speed. But this creates a different problem. The travelers would arrive at their destination decades or centuries after they left. But from Earth's perspective, even more time would have passed. They would be stepping into a future Earth, assuming they ever returned, where everyone they knew was long dead, and society had changed beyond recognition. And this assumes speeds we cannot currently achieve. This assumes propulsion systems that might not be physically possible. This assumes energy sources we do not have. This assumes materials that can withstand the stresses of near light speed travel. This assumes solutions to radiation shielding, life support, navigation, and countless other problems we have not solved. The light year is not just a measurement. It is a prison of sorts built from the fundamental speed limit of reality. Light moves at 300,000 kilometers per second, and nothing with mass can reach that speed. Everything must travel slower. And at slower speeds, even the nearest stars are unreachable within human lifetimes. Unless physics allows shortcuts, wormholes, hypothetical tunnels through space-time that connect distant points. Warp drives, theoretical methods of contracting space in front of a spacecraft and expanding it behind, allowing faster-than-light travel without actually exceeding light speed locally. Alcubierre drives, exotic matter with negative energy density. These concepts exist in mathematics and speculation, but there is no evidence they are possible in reality. No experiment has demonstrated them. No theory has shown they are practical. For now, stars remain unreachable. And yet, we continue to observe, to measure, to wonder. The light year exists because we needed it, because kilometers and miles failed, because the numbers grew too large, too abstract, too disconnected from anything the human mind could comprehend. 1,000,000,000,000 kilometers means nothing. 10 trillion kilometers means nothing. The brain cannot hold numbers that size. It cannot visualize them. It cannot relate them to lived experience. So astronomers converted distance into time. They measured how long light, moving at its constant speed, takes to cross the void. And in doing so, they created a unit that is slightly more graspable. Not easy to understand, not intuitive, but workable. A light year tells you something meaningful. It tells you that the object you are observing is so far away that light, the fastest thing in the universe, needed an entire year to reach you from there. It tells you that you are looking 1 year into the past. The light arriving at your telescope tonight left its source 365 days ago. This time-based framework helps. It gives context. It transforms raw distance, which is hard to grasp, into duration, which is something we experience constantly. You understand what a year feels like. You have lived through many of them. You know how long it takes for seasons to cycle, for birthdays to come around again, for the Earth to complete one orbit around the Sun. And when you hear that a star is 10 light years away, you can anchor that information to your sense of time. 10 years, a decade. That is how long light has been traveling from that star to reach you. You were 10 years younger when that light began its journey. The world was different. Your life was different. And yet, the photons kept moving, crossing the emptiness of space until they finally reached Earth. Compare this to saying the star is roughly 95 trillion kilometers away. That number is accurate, but it is useless. Your brain sees a pile of zeros and gives up. There is no connection to anything real, no way to internalize it. The light year, by converting that distance into time, makes it slightly less abstract. Astronomers also use other units. The parsec, for instance, which is based on parallax measurements and equals roughly 3.26 light years. The astronomical unit, which is the average distance from Earth to the Sun, about 150 million kilometers. These units serve specific purposes in calculations and observations. But for communicating with the public, for explaining cosmic distances to people who are not professional astronomers, the light year remains the most effective. It also unifies distance and observation in a way that other units do not. When you say a galaxy is 1 billion light years away, you are simultaneously describing its distance and its age in your observation. You are saying that the galaxy is far enough that light took 1 billion years to reach you, and therefore you are seeing that galaxy as it was 1 billion years ago. Distance equals history. Space equals time. The two are inseparable. This is one of the profound insights of modern astronomy. The universe does not just exist in space. It exists in space-time, a four-dimensional fabric where space and time are woven together, and light, moving at its fixed speed through this fabric, is the thread that connects observations to history. The light year makes this connection explicit. It is not just a distance, it is a temporal marker. It tells you when, not just where. And in a universe where we can never observe the present state of anything beyond our immediate neighborhood, this temporal information is critical. There's an irony here, though. We created the light year to make cosmic distances comprehensible, to give ourselves a framework for thinking about the vast scales involved. But even with this framework, the distances remain incomprehensible. 9.5 trillion kilometers per light year. Millions of light years to nearby galaxies. Billions of light years to the edge of the observable universe. The numbers are still too large. The scales still too vast. The light year doesn't make space smaller. It doesn't shrink the cosmos down to human proportions. It just gives us a language for talking about distances that exceed our ability to truly grasp them. It's a conceptual tool, a measuring stick for the immeasurable. And yet, despite the incomprehensibility, despite the impossibility of truly visualizing these distances, the light year allows us to make progress. It allows astronomers to communicate their findings, to compare distances, to map the universe, to understand its structure and evolution. Without the light year or something like it, cosmology would be far more difficult. Imagine trying to discuss the distance to Andromeda in kilometers, 23 trillion, 652 billion kilometers approximately. The number is unwieldy, awkward, hard to remember, hard to compare to other distances. But 2.5 million light years is simple, clear, easy to work with. The light year also reminds us of our limitations. Every time we use it, we're acknowledging that we're bound by the speed of light, that we can't travel faster, that we can't observe the present. That distance and time are fundamentally linked in ways we can't escape. We measure in light years not because it makes distances smaller, but because it makes them meaningful. It transforms empty space into narrative. Every light year is a year of history, frozen in the light traveling toward us. Every observation is a window into the past, and the light year tells us how deep that window goes. It's a human invention, of course, an arbitrary unit based on our planet's orbital period and the speed of light in a vacuum. Alien civilizations, if they exist, likely use different units based on their own planets and their own conventions. But the principle would be the same. Distance measured in time. Space measured in the duration of light's journey. Because at cosmic scales, there's no other way to make sense of it. We created the light year not because it makes distances smaller, but because it makes them meaningful. It transforms empty space into narrative. Every light year is a year of history, frozen in the light traveling toward us. Light years measure more than distance. They measure isolation. They measure the fundamental separateness of everything beyond our solar system. We are here. Everything else is there, and the gap between here and there is measured in years of light travel, years of emptiness, years of void. Proxima Centauri, the nearest star, is 4.25 light years away. That's 4.25 years of space between us and them. 4.25 years during which nothing exists but vacuum and the occasional stray hydrogen atom. No planets, no asteroids, no dust clouds. Just empty space, stretching on and on, light year after light year. This isolation is permanent. Unless physics allows something we don't currently understand, unless there are shortcuts through space-time we haven't discovered, the stars will remain out of reach. We can observe them. We can study them. We can learn about their composition, their temperature, their age, their life cycle. But we cannot visit them, not in any time frame that matters to human civilization. We are alone on this small planet, orbiting an average star, in a quiet corner of an ordinary galaxy. The nearest other stars are so far away that even light, moving at maximum speed, takes years to cross the distance. And we, bound by the laws of physics, can only move slower than light. Much slower. But here's the other side of that isolation. We are connected, not physically, not in any way that allows communication or travel, but connected by the light itself. Ancient photons link us to distant worlds. When you look at a star, you're receiving light that left that star years ago, decades ago, centuries ago. That light has crossed the void, survived the journey through interstellar space, and arrived at your eye. You and that star are connected by that photon, separated by distance but joined by light. Every star you see in the night sky is a portal to the past, not metaphorically, literally. The light is old. It carries information from a time when the star was younger, when the universe was different, when Earth was in a different state. And you, standing here in the present, receive that information. You witness history directly. There's something profound in that. Something beautiful even. We may be isolated by light years of empty space, but we're also participants in a cosmic conversation that spans time as well as distance. The universe is speaking to us through light, ancient light. Light that has traveled for years or millennia or billions of years to reach us. And we, with our telescopes and our eyes and our capacity for wonder, are listening. Humans are unique as far as we know in our ability to comprehend this. We can understand what a light year means. We can grasp, at least intellectually, that distance and time are connected. We can look at a star and know that we're seeing the past. We're aware of our cosmic address. We know where we are in space and time. We understand our isolation and our connections simultaneously. This awareness is a privilege. Most life, if it exists elsewhere, probably doesn't have it. Most organisms on Earth don't contemplate the stars. They don't wonder about distance or light travel time or the age of photons. But we do. We ask these questions. We build telescopes to see farther. We develop theories to explain what we observe. We measure the universe in light years and try to make sense of the incomprehensible. The light year measures not just space, but the universe's story. Every light year is a chapter. Every photon is a sentence. And we, here on Earth, are reading that story one observation at a time. We are piecing together the history of the cosmos by collecting ancient light and analyzing what it tells us. The stars you see tonight are not as they are. They are as they were. Some of them have moved since their light left. Some have changed color as they have aged. Some have exploded, though their final light has not reached us yet. The night sky is a patchwork of different moments, different eras, all layered on top of each other and visible simultaneously. because light travels at a finite speed. This is the nature of our universe. Distance creates delay, observation creates history, and light, moving at its unchanging pace, stitches it all together into the panorama we see when we look up. We may be trapped by distance. We may be confined to this solar system for the foreseeable future, perhaps forever. The light years that separate us from other stars may prove to be an insurmountable barrier. But our minds are not trapped. Our understanding is not confined. We can travel anywhere light has been. We can observe the distant past. We can study galaxies billions of light years away and learn about the early universe. We can peer back to within hundreds of thousands of years of the Big Bang and see the cosmos in its infancy. Light years are not just a measurement of distance. They are a measurement of time, of history, of the fundamental structure of the universe. They remind us that space and time are inseparable, that observation is never instantaneous, that everything we see is a glimpse into the past. And they remind us of both our smallness and our significance. Small because we occupy a tiny planet in a vast cosmos, measured in billions of light years. Significant because we are aware of that vastness. We understand it. We study it. We wonder about it. The light that reaches your eyes tonight left distant stars years ago. It has traveled through the emptiness of space, crossing light years of void, to arrive at this moment. And you are here to receive it. You are here to witness the universe's story, told in photons delivered across time and space. We may be isolated by light years, but we are connected by light itself. And that connection, fragile as it is enough to observe, enough to learn, enough to wonder, enough to understand that we are part of something vast and ancient and beautiful, even if we can never cross the distances that separate us from the rest of it.